All right, welcome everybody. So in this video, we are going to continue our exploration of bases and vector spaces. And in particular, what we're going to see is that no matter how abstract our vector space might be, we've seen vector spaces of functions and matrices, that these vector spaces, once we define a basis, they're going to look just like Rn, and our vectors, we can express our abstract looking vectors as column vectors, and then we'll be able to use a lot of nice results from linear algebra using matrices and vectors. So to get things started, let's just review the definition of a basis. And so if I have some subspace H of a larger vector space B, then a set of vectors from this vector space V is going to form a basis for this subspace if this set of vectors is linearly independent. So in other words, no vector in the set can be written as a linear combination of the other vectors in the set, and the subspace spanned by the set of vectors B equals all of the space H. And so with an example in R3, this set of 5 column vectors would not form a basis for all of R3 because they violate this first property. These vectors are not all linearly independent. If I tried to pick a set of these 2 vectors, though they might form a basis for a subspace of R3, they don't form a basis for all of R3. So this would not be a basis for R3. However, if we add one more vector, the third standard column vector, then we have a winner. And so this set of 3 standard column vectors is the standard basis for R3. Okay, so now that we've refreshed our memories for what the definition of a basis is, we've looked at an example here. Let's take a look at why bases may be particularly useful. And so the first nice result that we'll see for choosing a basis B on some vector space V is that it imposes a coordinate system on that vector space. So let's consider the vector space V of all 2 by 2 matrices with the usual operations. Then we've seen that this set of 4 matrices forms a basis for this vector space of 2 by 2 matrices. And so now if I have some general matrix from this vector space, so say for example, I pick a 2 by 2 matrix whose top row is 2 minus 5 and the bottom row is 17, 8. Then we can write this matrix, this element of the vector space, as a linear combination of these basis elements, right? Because these basis elements span all of the vector space. So given any vector in the vector space, we should be able to find weights so that when we combine these basis elements, we get our matrix, our 2 by 2 matrix back. So in this case, we can multiply V1 by 2. That gets a 2 over here. V2 gets multiplied by minus 5 to get a minus 5 in this position of the matrix. We multiply V3, which is this matrix over here, by 17 to get the 17 in this spot. And then finally, we multiply this last basis vector by the weight minus 8 to get the minus 8 in this entry in the matrix. And this has a very similar geometry to R4 in this case. So V is equal to R4, and we pick the standard basis for R4, then this matrix in this more abstract looking vector space is going to look just like this column vector 2, minus 5, 17, minus 8 in R4. And so on the next slide, we're going to prove a really nice theorem from linear algebra called the uniqueness representation theorem. And what we're going to show is that once we choose a basis for this vector space V, then for any given element in that vector space, the weights that we pick are going to be unique. So given this basis and this matrix in the vector space, there's no other combination of weights that we could pick that's going to give us back this matrix. Okay, so here is a statement of this theorem. which is the uniqueness representation theorem. So if we have a basis B that consists of n different vectors in the space V, and these vectors, they could be matrices, they could be functions, they could be whatever depending on our vector space. Then for each vector x in this vector space V, there exists a unique set of scalars, these weights, that we call our coordinates, such that we can write x as a linear combination of these basis elements. And the proof of this theorem is pretty nice and short and sweet. So let's go through that together. So let's since this basis B spans all of the vector space V, then we know that there are some scalars so that this equation up here holds. So in other words, since we have a basis, that means we know that we can write x as some linear combination of those basis elements. But let's suppose that that representation is not unique. So let's assume that there exists some other set of scalars of coordinates that we'll call d1, d2, up to dn, so that using those scalars and combining the same basis vectors gives us this same element x back. And so let's see why this would be problematic. If we take these two equations, so what we have up here in equation 1, and subtract from it equation 2, then on the left side, x minus x is going to give us the 0 vector. And on the right side, we could group our terms. So in front of basis element 1, we have c1 minus d1. And in front of basis element 2, we now have c2, d2, and so on. So now we have a homogeneous equation here. And these b's are forming a basis. And since we assumed that these vectors b1, b2, up to bn form a basis for v, we know that these vectors are linearly independent. And if these vectors are linearly independent, then this homogeneous equation has only a trivial solution. So that means this weight is 0, which tells us c1 is equal to d1. This should be 0, so c2 is equal to d2, and so on. So what we see is that for all j, the weights cj that we have equal all of the weights dj. And that is implying that this representation must be exactly the same as the first representation. In other words, this is a unique set of scalars that we find.